Similar triangles.
Similar triangles, yeah. Okay, we're going to look at similar triangles. Now, many of you have already done this, so it's a little anticlimactic, but what we're going to do is we're going to take the proportion stuff that we've already talked about, and we've talked about what it means to be similar polygons, right? Didn't we say the other day that if two shapes, two polygons are similar, then that means that all of their angles have to be congruent, right? And the corresponding sides are all going to be proportional. There's a word we use for that, scale factor. If we take if we have two versions of the same shape, same polygon, one is big and one is small, then the number that tells us how many times bigger the big one is called the scale factor, right? It's the number that tells us what is that size difference between those similar triangles. So what we're going to do today is we're going to take all that stuff we've already talked about and you've worked on, and we're going to get more specific with triangles. And so for 8.4 and then later on for 8.5, we're going to look at how we can do some stuff with focusing specifically on triangles. All right, so the first thing is, well, if we're told in this case here that the little triangle, or the big triangle, BTW, is similar to the little triangle, ETC, then we want to do some stuff. We want to write up a proportionality statement. We want to come up with a scale factor. And then once we do that, we're going to find some stuff, some missing information. We want to know what's the measure of angle TEC, and find some side lengths. Find side length ET and side length B, and segment length BE, the length of that segment. Okay. Now, so to do this, let me take a screenshot of this so we can write on it a little better. All right, so first things first. Okay, when we've got a situation like this where, do you see the two triangles that are similar? Let me everybody put all their phones. The two triangles that are similar, we've got that little one that's sitting on top of the big one. One thing that's convenient to do sometimes is to separate the two, to draw them as two different triangles. So let's do that. Let's take the big triangle, BTW. Okay, maybe that's good enough. B, T, W, and then we get this little triangle, scaled down version, that is E, T, C. And we know some stuff here. We're told that this top angle is 34 degrees. Bottom angle is 79 degrees. Okay, so what's the measure of that angle right there? 34, sure. Because they're the same angle, aren't they? They share the same angle, right? So what is the, if we, let's write in the side lengths too. We know that this is 3. We know that the whole thing is 20. Okay, and this is 12. Okay, can you identify what's the scale factor? 1 to 4. So small to big would be 1 to 4. Anybody else want to see how we get that? Explain how we get it. How do we get it? Okay, anybody else know? How do we get the scale factor? Say it again. 3 to 12. Sure. We have to find two corresponding parts, right? So the parts that would be the same, if I, for example, if I blew up the small triangle, if I scaled it up so they were the same size, is there one of those sides that would end up being, overlapping with the corresponding side for which I know the side lengths? I said that in a real twisted, probably confusing way. Let me say it again. Can you see two numbers up here? Two lengths of sides that go together, two corresponding sides. 3 and 12, sure. Right, we've got the 3 and the 12, because those those both go with the base of that triangle, right? Okay. So those are the ones I can use to determine, what's the size, relative size difference, the scale factor. Okay, so the scale factor would be big to small. We know that 12 over 3 is just 4 over 1. There it is. So the scale factor is 4.
Does it matter if you go small?
As long as you're consistent, it doesn't matter. The question might, like on Moodle, when you're answering a question, it might specify. It might say, what's the scale factor? What's the ratio of BW to EC? And then you'd have to go big to small because it asked you for the big first and then the small. But otherwise, if it doesn't specify, as long as you're consistent, you do the same thing. It doesn't matter. Okay. All right. So we got the scale factor. Now, what's going to be the measure of angle TEC? So we want to know what's the measure of that angle right there going to be. It's going to be 79. How come 79? You're right. Why is it 79? Because the angles, similar figures, have to have congruent angles. The angle relationships all stay the same when something gets bigger. Now, I'm going to give you an example of that. If I take a triangle here, watch something. I can't remember if I did this yesterday or not, but this is good to see. There we go. Yeah, now watch. If I scale this thing up, notice what happens to the angles. They stay the same, right? The sides get bigger, but the angles all stay the same, right? Does that make sense? Okay, so we know then, yeah, sure, we know that this has to be 79 degrees. How could I find the length of ET? And I always, if I'm looking for an unknown, in the unknown side length at least, in a situation where I've got similar figures, I am always setting up a proportion equation, a ratio equation, right? And then I'll just cross multiply and solve. So what's the ratio equation going to be here? I have to do, this to that must equal this to that. So I already know one this to that, don't I?
So 4 to 1.
There you go, right? We know that any linear measurement, anything that I can measure with a tape measure, right? On this triangle versus this triangle, I know it's going to fall in this ratio. That's the scale factor. So I know that big to small is 4 to 1. If big to small is 4 to 1, then here are some corresponding sides. Let's look at the red sides. That red side goes with that red side, right? So if I call this one X, let's just say, give it a convenient name, then I know that 4 to 1 must equal 20 to X. And X is what I'm looking for. X is ET, isn't it? Right? So how do I solve that ratio equation? Cross multiply. There's the equation. If I cross multiply, the first cross gives me 4X equals, on the other side, the other cross gives me 20. So what's X? 5. Right? So there's the length of ET. So, write it down here. So ET equals 5. Okay, they also want to know what's the length of BE. Well, look, BE is that segment right there. So how do we piece that together? And this goes way back to the beginning of the year. If I have segment BT is 20, but I just found that ET is 5, 15, right? Because they have to add 20, don't they? Segment addition postulate, beginning of the year. Okay? Make sense? Okay, we got it. No big deal. All right. Okay, what about this one here? What they're giving us in this case, now remember, you got to go back a little bit. The way that this will make sense to you is if we compare it to stuff we've already done. Remember, if we go back, boy, it's been many chapters ago, been probably three units ago, where we were talking about triangle congruence. We were proving triangle congruence. We had a bunch of congruence relationships. We had, for example, side, side, side. If the 3 sides of one triangle are congruent to 3 sides of another triangle, then the triangles are congruent. Now, what's another one we had? SSS. Another one we had. SAS, side angle side. If two sides and the included angle of one triangle are congruent to the corresponding, two sides and the included angle of another triangle, then those triangles are congruent, et cetera, et cetera. So we had 4 of them. SSS, SAS, ASA, and remember the 2 you can't have. Angle, angle, angle doesn't work, right? Because they don't have to be the same size then. And of course, the other one that we know about doesn't work, right? ASS doesn't work. So that only leaves AAS, angle, angle, side. Okay, so we had those 4. Now, what we're going to get for similarity relationships, we get similar stuff, right? We're going to get, instead of saying that the conclusion being that the 2 triangles are congruent, our conclusion for these relationships is going to be that the 2 triangles are similar. Well, one of them is AA similarity. Angle-angle similarity postulate says that if 2 angles of one triangle are congruent to 2 triangles of another triangle, 2 angles of another triangle, then those triangles must be similar. And that makes sense, doesn't it? Because if two angles are congruent, and the sum of the angles has to be 180 for both triangles, doesn't that mean the third one, we get the third one for free? Doesn't it also have to be the same? Right? If these 2 are the same as these 2, then the remaining, the leftovers that add up to 180 would also have to be the same. Okay? So we get that one. We're going to get 2 more in 8.5 that I'm not going to introduce right now, but they're coming soon. Let's take a look at this now. What I want to do, kind of last thing I want to take a quick look at. Thank you. Last thing I want to take a quick look at is using this angle-angle similarity relationship to show why it is that a line, that any 2 points I use to determine the slope of a line always give me the same answer. I think this, now I want you to just allow yourself to be interested in this for a second. This is something that's, you've been told this before, but this is, to me, it's really interesting and important that math does this kind of thing I'm about to show you. You've been told a billion times that 2 points define a line, right? All it takes is 2 points to define a unique line. There's only one line that goes through 2 points, is another way of saying that. You've also been told that it doesn't matter which 2 points you use to calculate a slope, you always get the same answer, right? And you've remembered those, and you've used it, and you're doing great with it. But I want you to see maybe another way of looking at that, that'll help you not only understand that it works, but maybe why it works. This has to do with some stuff we're going to talk about in Algebra 2 next year. If we take linear graphs, linear functions, we can graph, there's an infinite number of lines that I could graph on the board, on the XY plane, right? And if I draw a little XY plane, just to kind of illustrate this, it doesn't look, oops, it's not what I want. I want that. So there's my XY plane. If I draw some line, oops, I won't do that either. I want to do that. Make it a nice line. How about it? If I draw some line, then by controlling, there's 2 things. There's 2 dials that I could control to tweak that line to become any possible line. All of the infinite possibilities I can dial in by just controlling 2 numbers, the slope and the y-intercept, right? If I change the slope, then effectively what I'm doing is just changing the slantiness of the line, right? If I change the y-intercept, what I'm doing is I'm changing how high or low it is. Now, moving it left and right, if I move it like this, am I really changing the line? No, I'm not, because the line is infinite, right? It goes forever, doesn't it? Okay. I can't draw an infinite line, but pretend this one is, right? So the y-intercept then and the slope is all I need, those 2 numbers, m and b, to dial that in. Now, if I move to a more complicated shape, like we're going to do in Algebra 2, we're going to talk about some of this stuff next year where, let's say we've got a, can I draw this? Kind of doubt I can draw it. That's going to work. Oh, maybe I can't. cool. Okay, I can draw a parabola. Okay, that's the graph of a quadratic function, it's a parabola. Now with a parabola, that's more complicated because it's not just straight, it's curvy, right? So I need more numbers to dial that in. There's an infinite number of parabolas that I could graph on the xy plane also. But this time, instead of just two numbers, m and b, I need three numbers. And I can define those three numbers in different ways that we'll talk about next year. But what those three numbers are going to allow me to do is, if one number changes, then it gets skinnier. If that number changes differently, it gets wider. If that number changes even differently, then this thing could be flipped around so it's upside down. Okay. The other thing I can do is I can change two more numbers to determine where this thing is located horizontally and where it's located vertically. And once again, it goes forever, but I just can't draw it forever, right? So that's coming up next year. Now, going back to this line though, if one of these properties of the line is a slope, then that's a property of the line. It can't change. Any 2 points or any 3 points or any 10 points that I pick, it doesn't matter which points those are. If I take 2 points and I use those 2 points to calculate a slope, that slope is one of the numbers that I dialed in for that line. It's never going to change. It's a property of that line. It goes with it, all intrinsically. Okay. All right. So then, if we go back to this, is there a way that we can demonstrate that inherent property of the line, that it's not going to change, using geometry, not algebra, using geometry? There is. Look what we can do here. If I take this little triangle, BCE, and I compare that to the bigger triangle, ADF. Everybody see that? I got the little one. Let me make the little one in green. Okay, there it is. And here's the big one. Okay, those are similar, aren't they? They have to be similar because we know that, for example, those two angles are congruent and those two angles are congruent. So by angle-angle similarity, we know the triangles are similar, right? So the ratios of all the corresponding parts should be the same, right? Now let's look at the ratios specifically. Let's look at the ratios of height to height and width to width. In other words, if we thought of those in terms of slope, if an ant were to start off at this point right here and travel up to this point right there, walk along that small triangle, isn't the blue line going to be his rise during that journey, and the orange line is going to be his run? Agreed? And then for the big triangle, same thing. If I go from point A up to point D, now I get this bigger rise and this bigger run. But can we show that those two things are proportional? Easy. Here's all we have to do. Look, we know that the ratio of the two blue lines is just CE over DF, right? So height to height, small to big height must equal small to big width, right? So that's just BE over AF, right? That's our similarity statement. I know if the two triangles are similar, then the corresponding parts have to be proportional in the same fraction, right? Now I can use a property of proportions here. And look what I can do. I know that I can exchange diagonally. If I have a ratio equation, remember we learned some properties. One of them is that I can do an old switcheroo diagonally. So the BE is going to go down to the bottom of the first fraction, and the DF goes to the top of the second. So we end up with this new fraction. Well, look at that. CE over BE, so that's small height to small width must equal big height to big width. In other words, rise over run for the small triangle equals rise over run for the big triangle. How about that? We just showed it. By proportionality, those mean slope, don't they? both of those are equal to m. Okay? So a completely different twist on it. We didn't use algebra at all. We just used all geometry, but we just demonstrated that algebraic property. That probably isn't totally, I don't know, I hope you can see why that's pretty interesting that you can do that kind of stuff. That you can, you can take something you've been taught and you can look at it different ways, but you always come to the same conclusion. Math is so symmetrical that way. It's really, that's part of the beauty of math. All right.